Good morning, students. Today's topic of discussion is RBM, Restricted Boltzmann Machine. This is a very good article on RBM that I would be discussing. RBM, Restricted Boltzmann Machine. It is a variant of Boltzmann machine with a restriction that we would know as we go along. It was invented by Paul Smolensky in 1986 with the name harmonium. However, Geoffrey Hinton and his team, they have developed a faster variant of RBM, and they used it when they were designing this back propagation algorithm, and they devised a new architecture of RBM and used performed training on it. RBM is used in many applications like dimensionality reduction, collaborative filtering, feature engineering, regression classification, and topic modeling. Dimensionality reduction is about reducing the number of features that are used to perform the prediction or classification in a data set. Collaborative filtering uh, is about filtering of the features only using a collaborative method in which two or more features they perform together to identify or classify or to predict a particular aspect of data set. Feature learning, uh, if given a data set, which feature is more useful uh, in order to um, analyze that data set. That is feature learning. These three deals with feature engineering, for which RBM is quite useful. Regression classification is to predict a numeric value. Regression is all about giving out predictions in terms of numbers. For instance, house price. House price is a numeric value which is given by the model. Topic modeling is related to text mining, where given a paragraph or a document, its topic can be determined. So all this can be performed through RBM. RBM usually is used in unsupervised ways, and depending on the task, it can be used in supervised as well. RBM's architecture, it has got an input layer and a hidden layer. We have learned various architectures of neural networks. Uh, for instance, perceptron, and then feed forward neural network, and then artificial neural network, convolutional neural network, recurrent neural network, LSTM, GRU. These are different architectures of neural networks. These RBMs has only two layers. There are nodes in the first layer, which is the input layer, also known as visible layer. There are the nodes in the second layer, which are known as hidden layers. Hidden layer. It's not layers, it's just layer because there is only one hidden layer and these will be connected. So here, this is our RBM, restricted Boltzmann machine. It has got only two layers: input layer, also known as visible layer, and single hidden layer. And there is a restriction in terms of connection to these neurons or nodes. Neurons are connected only to the neurons in other layers, but not to the neurons within the same layer. Essentially, there are no connections among the visible neurons to visible neurons, and there are no connections among hidden neurons to hidden neurons. And therefore, this RBM visible and hidden neurons connections form a bipartite graph. Look at here, it looks like bipartite graph. Here, this connection is not possible, and also this one not allowed. Means these are the neurons or the nodes in the input layer. These cannot be connected among one another. All right. Uh, Apparently, these neurons in the hidden layer also cannot be connected. And therefore, the term restricted in RBM means that no two nodes in the same layer share a connection. And RBM looks like this. These are visible nodes. These are actually the input nodes from which it receives the input. And these are the hidden layers. And you see that each neuron in the visible node is connected to every other neuron in the hidden node, hidden layer. Means these hidden nodes, as you all are aware, neurons and nodes are synonymous. So hidden nodes or neurons, visible nodes or neurons, and their connection. How does RBM work? RBM works in two phases, uh, forward pass and backward pass. Backward pass is also known as reconstruction. This working is similar to the working of any neural network, which performs uh, training of the network through two phases. In the first phase, this forward pass, input travels from input layer to hidden layer to subsequent hidden layer, and you find that there is a consecutive uh, layers of um, nodes or neurons in between this input layer and this output layer. You can find a series of layers. Therefore, in this forward pass, input travels from this left direction to right direction. And in this backward pass, which is known as reconstruction here, weights are updated. Here, weights are updated. Here, input is processed. Okay, how it is processed? Input is processed by two operations, sum operation and activation function. All right. So, how RBM performs its operation? It takes inputs and translates them into a set of numbers that represent the input. All right. The set of numbers represent the inputs. This is done in the forward pass. Then these numbers are translated back to reconstruct the inputs. For instance, if I say that A stands for 1, in this input layer, you provide A, and then this A is represented by numbers, which is 1, and this process is forward pass. Then these numbers are translated back to reconstruct the input, which means that again this is forward pass. In the backward pass, this number is converted back to the input. All right, numbers are converted back to the input. In the backward pass, essentially this means that input is encoded, and uh, in the backward pass, this set of numbers, this set of numbers. For instance, you have A, B, C, several input values. These numbers, they are reconstructed to create the input back. So this that is known as reconstructed input. In this backward pass, this one is translated back to A. In the forward pass, A is translated to 1. And there are several forward and backward passes. When RBM network performs forward pass, backward pass in for n number of times, then it is said that RBM is trained, and later RBM can reconstruct the input data. Whatever input has been provided, that input can be reconstructed, and these there are three steps that are repeated over and over through the training process. This is the training process. Go forward, come back, forward, back. Like this is done for n times. And these three steps are repeated over and over through the training process. With a forward pass, every input is combined with an individual weight. These weights are global in every neural network. Every neural network has weights, uh, weights on the connections. When you have neurons or nodes, these neurons are connected. These connection lines carry a value which is quite significant in the learning process. And the whole idea of machine learning and deep learning depends on how these weights are updated, and eventually what are the values that these weights acquire through the learning process. Uh, this weight you will find on every connection. In RBMs, you have only two layers: input layer and hidden layer, or visible layer and hidden layer. Visible layer has connections to these hidden layers, and every connection has a weight and a bias. You know that there is a bias for every connection, and then the result is passed to the hidden layer, which may or may not activate. Here this input value is multiplied multiplied, or mm, some processing is done on input and this weights. Next, in the backward pass, each activation is combined with an individual weight and overall bias, and the result is passed to the visible layer for reconstruction. What happens is, um, A, for instance, A is converted to 1. How is A converted to 1? That this conversion process requires weights. All right. Uh, Further, when 1 is obtained, 1 is sent back to reconstruct the input, which is A. If in case the reconstruction does not create A, rather creates B, it implies that this these weights, okay, say here you have 1.1, or here any weight value. All right, initially you can start with a um, very minute value, a very small value, and later through this training process these weights gets updated, and they get their own values which are useful in reconstruction process. uh, well, here the what result you got here, the result is 1. From input A is transformed to 1. This conversion has to be done in such a manner that reconstruction yield the same input value. All right. And at the visible layer, the reconstruction is compared against the original input to determine the quality of the result. We know that our input is A, and if the reconstructed input is B, when you compare both, they are not equal. Because they are not equal, uh, it apparently means that this conversion process was not done in a proper manner. So then what has to be done? Again, A has to be converted to some value using a different weight. All right. Therefore, the weight is updated. This process is quite useful because you can encode the input in some form, and that form can be reconstructed back to its original form, which is our input. And this is a important point here. A trained RBM, when can we say that RBM has been trained? When it goes through this forward pass, backward pass number of times, and is able to recreate the input, then it is said to be a trained RBM. And trained RBM will reveal which features are the most important ones when detecting patterns. If I tell you that uh, a house price, okay, the price of the house is 1 lakh. How I am able to estimate this price as 1 lakh? This 1 lakh depends on some features. What might be the features? The primary feature might be the square feet area, and the next feature that might determine the price might be the this constructed year. When it is constructed, if it is constructed in this year or last year, obviously the price will be high because it is newly built house. And suppose that this two are the primary parameters to determine the price. These parameters are nothing but the features, significant features in a data set. All right. RBM could determine and reveal the features. These are not only features. If for a house you will have number of rooms, whether car parking is there or not, what is the water facility, and where is it located, locality, and there are several other features that uh, are relevant in coming up with the price. But then, out of all, not every feature is important. Few are significant ones that actually determine the price. And those features are the important ones generated by this trained RBM. And a well trained network, it will be able to perform the backward translation with a high degree of accuracy. And in both the steps, forward and backward, weights and biases have a quite important role to play. Uh, weights are only the ones that performs this conversion process. If there are no weights, how can you um, convert without performing any kind of processing? And to perform processing, you require two numbers, right? The first number is the input number, the second number is the weight. When both are processed, they obtain a converted value. If I say that 10 into 2 is equals to 20, this is our input, this is our converted form, for instance, and these are weights. To obtain the excuse me, sorry about that. And to obtain this 10 back, what do you have to do? This 20 has to be divided by 2. When you divide this 20 by 2, you get back 10. If this 10 is the input and 20 is the transformed uh, value, then from this transformed value, you are obtaining the input back. All right. Then Essentially, this RBM is part of a family of feature extractor neural networks. This essentially extracts the features. And these are also known as autoencoders. Why they are known as autoencoders? Because they encode their own structure. This A, B, C, these get encoded in some form. It can be 1, 2, 3, or some number. This is encoding. The network can perform this encoding. The difference between autoencoders we have already studied and RBMs is that RBM uses a stochastic approach. Stochastic approach means that it is not fixed, and therefore it cannot be determined. Whereas encoders uses deterministic approach, you can determine, okay, the time, the other aspects of this training. There is an example here, RBM. These are visible units. This is a bias. These are hidden units. There are vectors with 7 values. This 1, 2, 3, 4, 5, 6. The visible layer must have j is equals to 7. The second layer, which poses I neurons, here this should be 7 actually, because there are 7 input values, so there should be 7 input nodes. And then there are two, this hidden, how many nodes should be there in the hidden layer? This is not exactly same as the input. It is like a hyperparameter. It depends. And each hidden node can have a value of 0 or 1. And there is a probability that this logistic function of the input it receives from the other j visible units are called PSI equal to 1. Yeah, this probability is uh, specified, and each node in the visible layer also has a bias, and it is denoted by V underscore B, means visible layer bias. And visible layer bias is shared among all visible units. One bias unit is shared among all. And there is a there is a bias for hidden layer as well, and that is denoted by underscore B, means bias of hidden layer. And that only one bias is shared among all hidden layers. I mean hidden nodes. Look at here. This is how through TensorFlow it can be created. A vector of 7 and 2, and weights have to be defined between the visible layer node and the hidden layer node. And in the weight matrix, the number of rows are equal to the visible nodes and the number of columns are equal to the hidden nodes. Rows, here in this case there will be 7, and columns will be 2 because there are 2 hidden nodes and 7 visible nodes. and therefore you get a tensor of 7 by 2. And the number of neurons in visible layer, and 7 is the number of neurons in visible layer and 2 is the number of neurons in the hidden layer. In the forward pass, one training sample X given as input to all the visible nodes and pass it to the hidden nodes. And processing happens at each hidden layer node. And this computation begins by making stochastic decisions whether to transmit that input or not. Stochastic decisions are not fixed and cannot be determined. And at the hidden layers nodes, x is multiplied by wij, weight between node I and j, and added to the bias. The result of those two operations is fed into the sigmoid function. Here you can see wij into x, this weight and input value, multiply, and then you form this for every connection. If it is getting like this, then here what do you do? This x1, x2. Here you perform w. This is w1 to 1 into x1, and this w2 to 1 into x2. And that whatever you obtain, that this one you give as input to sigmoid function. Sigmoid function is also known as logistic function. That will yield this value, this phj, and it is the probabilities of the hidden units, and all values together are called probability distribution. And this RBM uses input x inputs to make predictions about hidden node activation. You see here, probability of h1 is equals to 1 given v. V is what? The vector. Is this. How is this obtained? This is obtained by performing that operation. And for each row in the training set, a vector or tensor is generated, which is here in this case 1 by 2. And totally n, there are n vectors. So P of h is equals to n into 2. All right. And then unit, this hidden unit with probability hj given v, conditioned on v, uh, and turn it off with probability 1 minus phj conditioned on v. Whatever value you get, if you get here 0.4, then if you subtract 1 minus 0.4, you get 0.6, like that. Therefore, the conditional probability of a configuration of h given v is this. Okay, p of h given v, that uh, you do for all total all the hidden units. Then you get probability of a hidden unit and hidden activation vector. Hidden activation vector is obtained by through this. Let's take an example, and then this example is this is the input vector, and these are the weights, and this matmal operation will perform weight into input, and the samples are drawn from the distribution, so uniform distribution is used, and then activation of hidden state is obtained. This backward pass reconstruction, this we will study tomorrow.